Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving an interesting equation, a homemade equation with complex numbers. Somebody probably came up with this problem before, but I haven't seen it anywhere. If you do, just let me know. Anyway, so we have a really complex equation. We have two unknowns, z and w. Z and w are complex numbers, by the way. And we have z to the w equals 1. So which complex numbers satisfy this equation? And can we find all the solutions? Or are there any solutions? I'm pretty sure you know some of the solutions, don't you? There are some trivial solutions, which I'm pretty sure you already know about. But we're going to be looking at those as well as the more interesting ones. All right, so let's go ahead and see how we can solve a problem like this. First of all, you can just go ahead and natural log both sides, right? And if you do, you're going to get something like this. ln z to the power w equals ln 1. Now, obviously, we didn't get into the complex stuff yet, but just think of it as a simple equation. You can move the w, you get w times ln z equals ln 1, which is 0, right? In the real world, at least. And then from here, you get two results. Either w is equal to 0 or ln z is equal to 0. Obviously, this implies that z is equal to 1, right? Because ln 1 is 0, and this implies w is equal to 0. And there's an or behind it. Can both of them be true at the same time? Absolutely. Once the base is 1, we don't really care about the exponent, do we? 1 to the power any number is 1. So this means that if w is equal to 1, if w is equal to 0, like z to the power 0, and we always get 1. And I know some people are thinking, okay, but as long as z does not equal 0, right? Wrong. Because 0 to the power 0 can also equal 1. You don't believe that? Go ahead and check out my video on my other channel. Do I have another channel? Yes, I do. My very first channel, actually, Cyber Math, which I focus on real numbers, you know, trigonometry, number theory, a tiny bit of geometry. But this channel focuses on complex numbers. Anyways, so you can go and check it out and let me know what you think. I'll try to share the link here for that video that I made for 0 to the power 0. And I know some people are never convinced, but that's okay. So these are kind of like trivial solutions again, right? They're not very interesting. They don't really give us a lot of insight into the world of complex numbers. So maybe we should do something much more complicated. And that's what makes this video real fun. Okay, let's take a look at it from another angle. Z to the power w equals 1. And we just ln both sides, right? But we only considered a single value for 1. What is that supposed to mean? Well, in the complex world, you can express 1 in infinitely many ways. And we'll talk about that. So let's go ahead and do this. First of all, let's talk about the complex exponential. You know, in the real world, you can probably define, right, hopefully, something like 2 to the third power. You write the 2 3 times and multiply. Or something like 3 to the power 1/2, you can define it as the square root, so on and so forth. And if you have anything like 5 to the power square root of 2, then you can approximate square root of 2, make it super close to a rational number, and the rational numbers means a radical, so on and so forth, right? So you can make it converge. But what about the complex world? When the base and the exponent are both complex numbers, things aren't that simple. So we have to play the game by the rules, and there's a way to write z to the power w in the complex world, and this is how it is. We can write it as e to the power w ln z. Notice that this goes here, and z goes here. And then the right-hand side, this is where we have the complexification of 1. Big word, right? You can write the 1 as e to the power 2 pi n I. This just comes from the fact that, thanks to Euler, we have a polar form of a complex number. So anytime we write something like e to the I theta, this basically represents a complex number which makes an angle of theta with the x-axis, which we normally call the real axis. So this is the real axis, this is the imaginary axis, and e to the I theta gives us the number. But there's also another component, which is r, and that will be the distance from 0, which is also called the modulus or the absolute value for this complex number. With R, the number actually will be complete. We have everything we have. Okay? I mean, we have everything we need. That's what I meant. So we were able to write a complex number as an exponential, which is nice. And then when you expand e to the I theta, you can also write this number as cosine theta plus I sine theta. Of course, I didn't include r. You can just multiply the whole thing by r. But this also gives you an opportunity, along with the r, let's say you're trying to write this number, then you would have r cosine theta plus I times r sine theta. And if you call this a and b, then you're basically talking about a plus bi, which is the name of this channel. A is the real part, B is the imaginary part, so on and so forth. So I kind of give you a quick summary of all the lecture videos, not all of them, but at least some of them. And if you want more details, go ahead and check out my lecture videos, particularly if you are new to complex numbers. But here's what we're going to do. Once we get this equation, actually we're in good shape because notice that both sides are exponential. And so let's go ahead and just copy that equation here, e to the power w ln z. And remember, this comes from z to the power w, which is equal to 1, which is equal to 2 pi and I. Oh, by the way, I was just explaining why this is equal to 1. And this is why. When you write it as e to the power I times 2 pi n, of course, n is an integer. This is a multiple of 2 pi. You're basically talking about a number, complex number, whose angle is 2 pi or 0 or whatever, right? And that just represents a real number, a positive real number. And because the modulus is 1, or the radius, or the absolute value, it just represents 1. In other words, if you wanted to complexify 1, this is how you write it. Okay, to keep a long story short. So this is the piece we need for our solution. Let's go ahead and take that. And now since both sides have e, we can just write from here, w ln z is equal to 2 pi n I. This is where interesting stuff begins, if it wasn't interesting so far. Now, we're going to go ahead and look at several different solutions. But to be able to express this, like, you know, we want to find an equation or equations from here. So let's go ahead and do this. Let's just write z as r times e to the I theta and w as a plus bi. Okay? Great. Now, why did I do that? You'll see in a little bit why this is helpful. Because, let me tell you, we're going to be natural logging this. So when I do, it's going to turn into a standard form. If I use a complex number like c plus di, what would ln c plus di look like, right? That would be hard to deal with. So when you do this, obviously, we have to talk about there's infinitely many ways to express it, because theta can be theta plus 2 pi n. You can add multiples of 2 pi, but I'm just going to go with the principal argument. I'm assuming that theta, in this case, is the principal argument. So we ln both sides, and that also gives you a formula for the natural log of a complex number, or what is called the complex logarithm. Okay, so far so good? Okay, all of these were kind of like an intro. Now let's go ahead and put this into work. W ln z is going to equal then a plus bi multiplied by ln r plus I theta. Obviously, bi and ib are the same, but when it's I theta, when there's a theta, we usually write it that way. No big deal, commutative property. And we know that this is equal to what? 2 pi n I. Now, this is the most beautiful part, I think, because you know why? We have two complex numbers that are equal, okay? So this means a lot, okay? Let me tell you. So let's go ahead and use, the most important stuff that I always forget to say, I squared equals -1, because I is the square root of -1. But again, check out the lecture videos for details. Now let's go ahead and distribute this then. This is going to give us a ln r plus a theta I. And then this one is going to give me b ln r times I. And finally, when we multiply these, we're going to get I squared, which is going to give us a minus sign. And that'll be b theta, because I squared is -1. And this is equal to 2 pi n I. So far, so good? Now, here's what we're going to do. We're going to put the real parts together and the imaginary parts together, so we can compare a ln r minus b theta plus a theta plus b ln r. That will be the imaginary part of our complex number. But notice that On the right-hand side, we have an imaginary number, a number that is complex but not real, a number that has a real part 0, which means when you compare two complex numbers, obviously the real parts have to be equal. So this needs to equal 0. And once that cancels out, the imaginary part needs to equal the imaginary part, of course. So from here, we get a system of equations. How nice, right? No, not really, because we have a lot of variables. But don't worry, we're going to look at some interesting scenarios. So first of all, this gives us a ln r equals b theta. Great. And then second equation gives us a theta plus b ln r is equal to 2 pi n. N is an integer. Again, let me repeat that. So it can be many things. But for simplicity's sake, let's go ahead and take n equals 1. Can we take n equals 0? Yes, but you're not really going to get much out of it because that'll put you at 1 equals 1, which we already talked about. Okay, but n equals 1 is going to be actually a little more interesting. Let's go with that. If n is equal to 1, then second equation becomes a theta plus b ln r equals 2 pi. And the first equation just stays the same, a ln r equals b theta. And from here, you can do a couple different things, obviously. First of all, look at the number of variables, right? We have a, we have b, we have r, we have theta. They're not totally independent because obviously theta depends on, does it? I was going to say theta depends on a and b, but no, that's not the case. So never mind. I don't know what I'm talking about. But this system, we can solve under certain conditions. Of course, it's kind of like a system with parameters. So we can change some of the variables and kind of explore what that's going to look like. And I'm pretty sure there is a graphical explanation for this well, but it's probably going to be way too complicated. But let's go ahead and do this. For example, from the first equation, I can isolate b ln r and write it as 2 pi minus a theta. From the second equation, it's a ln r equals b theta. Then I can divide these equations. Ln r cancels out. From here, we get b over a. And then once we cross multiply, we get b squared theta equals 2 pi a minus a squared theta. And then we can put the a squared and b squared together, factor out the theta, and set it equal to 2 pi a. And from here, if you want, we can do a couple different things like a squared plus b squared divided by a is equal to 2 pi divided by theta. So at this point, you might assume something like, okay, what if theta is something, right? We can make some assumptions. And that's going to give us some interesting cases. Let me show you. For example, suppose, and again, we need to make an assumption so we can get a somewhat nicer equation. Suppose theta is equal to pi over 2. From here, we get a squared plus b squared divided by a equals 2 pi divided by pi over 2. As you know, this is equal to 4 because pi is going to cancel out. And then from here, we get the following equation, a squared plus b squared is equal to 4a. What does that equation look like? Remember, finding the a and b values is going to give you the w. So once you find a and b, from here you can find w. Let's go ahead and see how we can do that. I'm going to go ahead and subtract 4a from both sides. And then obviously, the next step would be to complete the square, add 4 to both sides, and then guess what this is going to become? This is going to become actually the equation of a circle. On the A, B coordinate system, you're basically talking about a circle whose center is at 2, 0, like this, and the radius is also 2 units. So we have a circle that is tangent to the, and I could probably do a better circle if I keep my, hopefully, right? Yay, I was able to. Well, the center is a little off, but hopefully we can fix that. Oops. Too bad. Go back, oops, and then make the eraser partial so it doesn't erase the whole thing when I do. Go back, and let's go ahead and erase this tiny bit. Okay, we're going to have to change the center a little bit to make it, you know, like better looking. Maybe put it somewhere here. Okay, so this is 2, 0. Let's just say this is 1, 0. We have a circle whose radius is 2 units. It's tangent to the y-axis, or should I say b-axis, because it's in A and B. Make sense? So what does this mean? it means that all the points on the circle, if theta is equal to pi over 2, which I'll show you what it means, then this equation, any point on the circle will be a solution. And if you remember, we said that W is equal to A plus BI. So if you pick a point from this circle, for example, 0, 2, right? 0, 2 would give you, let's see, would give you 2i, right? So W would be 2i, obviously. And then since theta is pi over 2, then we can just plug it in and find z. But z is r times e to the I theta. So we kind of need to know what I is, right? Or I mean, r is. Okay. So we said that a is equal to 0. This automatically actually turns b into 0. So that's kind of problematic. I don't know if this is going to work. Maybe pick something else. I don't think a equals 0 is going to be a good idea. Maybe pick something like, how about this? We have point 2, 2, right? On the circle. Let's try that. 2, 2 means a is 2, b is 2. So from here, we get w equals 2 plus 2i. And z is going to be r times e to the I theta. And we said that theta is pi over 2, so this is going to be r times e to the I pi over 2. You got to remember, this is I, so z is going to be ri. But what is r? Let's go ahead and find out. If a and b are both equal to 2, then let's see. If a is equal to 2 and b is equal to 2, and theta is pi over 2, so we're going to get 2 times ln r is equal to 2 times pi over 2. And then 2 is going to cancel out. We're going to get ln r is equal to pi over 2, which means r is e to the power pi over 2. So that's some number. That's a real number, right? R is going to be e to the power pi over 2. So we get e to the power pi over 2 plus I times pi over 2 as our z. And then raise it to the power w, which is 2 plus 2i. And that's for you to do the work to show that this is indeed equal to 1. And if you ask this question to Wolfram Alpha, it doesn't even understand what the question is trying to say. Too bad for an LLM, right? Humans are still smarter than machines and AI and all kinds of things like that. Anyways, this brings us to the end of this video. Well, thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care. Don't forget to check out Cyber Math, the Shorts channel, aplusbi, and bye-bye.